Marco and Kunal, they are working at Los Alamos, and I mean it's a group there with Patrick Coles, and for last few months they have published a few papers on near-term quantum computing, trainability, and this kind of stuff. So I think first probably Marco will present, and then Kunal will present. And Kunal is a PhD student with, I think, Mark Wilder at LSU. So it's a great pleasure to have these people around here. And I think we will have a nice talk. So if you have any question or something, you can put it in chat, or like towards the end you can ask. Yeah. So Marco.
Well, thank you very much. First of all, thanks to Kishore and Hermione for organizing this and inviting us. It is a great opportunity to be able to share our work here with us. As I was introduced, my name is Marco, and I'm a postdoc here at Los Alamos National Laboratory. And I have the pleasure of sharing this talk with Kunal Sharma that has been working with us since February, I believe. And during this time, we've managed to keep working and pushing this work on trainability of quantum neural networks that we're going to be telling you about. So I'm not really sure, can you see the mouse if I move it around?
Yeah, can see that.
Okay, perfect. I might use that just to point to certain things, so it's good to know. So yeah, the two works that we're going to be talking about were both of them uploaded to the archive this year. The first of them was in collaboration with two other postdocs here at Los Alamos, Akira Sone and Tyler Volkov, and two staff scientists, Luca Alcincio and Patrick Coles. And the second work that we uploaded just a month ago was done in collaboration with Kunal as part of his work here at Los Alamos. So let me first start by introducing some probably very basic concepts. Essentially, the goal of this talk is about talking about quantum neural networks in the NISQ era. So first, let me just take a step backwards and talk about classical neural network. So as many of you know, probably many of you are way more experts than me on classical neural networks. Classical neural networks are widely used today, and we know that they have impacted and have many revolutionary applications in many fields across science. Now, the main idea is that nowadays there's big push to develop near-term quantum computers. We have big companies as IBM, as Google, as Rigetti, that are trying to develop near-term quantum computers that already have of the order of tens of qubits. Now, the question is, how can we use those quantum computers to try to generalize classical neural networks and create what we call quantum neural networks? And basically the hope is that by just exploiting the power of those quantum computers, we might be able to outperform classical neural networks on some machine learning tasks. And of course, this should be particularly true whenever we're talking about quantum data or tasks that are quantum in nature. And let me just take a step back here and say that whenever I talk about quantum data, I mean that we have some quantum neural network that is mapping quantum states to quantum states. And as we all know, simulating quantum states takes exponentially many resources. The more qubits we need to simulate, the more resources we have to take. So of course, this is the sort of tasks that we try to employ a quantum computer for. Now, the question, once all of this has been said, is what is a quantum neural network, right? What do we call a quantum neural network? Unfortunately, I can give you a very simple definition, which is, let's just take a classical neural network as a computational model and try to generalize this so that it uses the principles of quantum mechanics, and hopefully we can use some of the advantages that have been proven for quantum computing to gain some advantage over classical neural networks. Of course, this in practice, just like in the classical case, there is not a single realization of what we call a quantum neural network. There's many realizations. And in particular, the first part of the talk that I'm going to be focusing on, is going to be focusing on what we call variational quantum algorithms. Now, I'm not really sure what the scope of the audience is, so I might go a little bit slow in this part for some of you. If that's the case, please bear with me. So one of the most promising applications in the NISQ era for quantum computers are what we call variational quantum algorithms. So the main idea of variational quantum algorithms is that we have a quantum computer. This quantum computer, as the name NISQ entails, is going to be noisy, is going to have a limited depth of what we can, of the algorithm that we can run, and it's going to have a limited number of qubits that we can work with. But still, maybe there is something to gain with this quantum computer. So the goal of variational quantum algorithms is to employ our faulty, noisy quantum devices and still try to gain something out of them. And we do this by what we call hybrid computation, where we harness the power of quantum computing to do what we cannot classically simulate, which is large quantum states. Oh, sorry about that. And then we employ a classical computer. Now, the main goal of this is that we have some tasks. So now we can prepare some state on a quantum computer. And this state, we're going to send it through a circuit, what we usually call a parametrized gate sequence. Now, this is where you can start to see why we say that variational quantum algorithms are some sort of realization of quantum neural networks. Because in our circuit, and you might have seen like many textbook circuits for quantum mechanics, and many of them have gates acting on them. Some of them might be rotations, and they might have a parameter on them. Some of them might not have parameters like a C0 or a control Z. And the whole combination of gates that we act is going to make this gigantic circuit and a unitary, which in this case I'm going to call V of theta. So this theta right here is just some hyperparameter that describes my quantum circuit. This theta can have continuous variables like a rotation angle. I'm doing a rotation around the y-axis on one of the qubits. And this angle is going to, in this rotation, is going to have an angle that defines this rotation. But it can also have discrete variables like the placement of gates or the type of gates that I'm doing in the circuit, because whenever I define a circuit, I not only have to define which are the operations that I'm making, but I'm also going to have to define which is the qubit that I'm going to be acting on. So this gate sequence that we have here, we usually call this a parametrized quantum circuit. It's going to depend on discrete or continuous parameters. And we have some tasks that we were trying to solve. And of course, the most famous example is the variational quantum state eigensolver, where what we want to do is we want to try to prepare the ground state of a given Hamiltonian that could have some information about protein folding or have some information about the ground state of a molecule that we're trying to solve. So the goal is that we're going to take a quantum computer, we're going to take a state, what I here call a rho, and in general, it could be a pure state or a mixed state, and we're going to send it through this parametrized gate sequence. We're going to do all of this rotation angles and fixed gates. And at the end, we're going to make some measurements on the state that we obtain. And hopefully with those measurements, we're going to be able to get some information about the problem that we're going to try to solve. And for this, we actually need to define what we call a cost function. That is going to define how well our gate sequence is performing for the task that we're trying to solve. So for VQE, the cost function is just the expectation value of the Hamiltonian, i.e. the energy of the state that we're trying to solve. And the lower the energy, the better it is. So what we're going to do, and this is why it's called hybrid, is that we're going to use quantum computer for the hard part, which is just create a quantum state, apply some gates, and make some measurements. And this cost function, which is just a single valued, usually real function, we're going to input this into a classical computer for an optimization loop, because the problem that we're trying to solve is this minimization. We're trying to find the minimum set of discrete and continuous variables in my parametrized gate sequence to try to solve the problem at hand. So we usually say to the classical computer, these are the angles that I employed. This is the cost function value. Can you give me new angles that are going to try to minimize this cost function value? And we're going to go about this optimization loop trying to find the best parameters for our parametrized gate sequence. So as you can see in this sort of scenario, wherever I have just a circuit with rotations angles in it, I have some parameters that I'm trying to find. Now, of course, you might say this variational architecture, it might not look like the classical neural networks that we're used to. It's just some realization, right? But of course, there's many more quantum neural network architectures, and we're going to be talking about some of them. For instance, we can actually define quantum perceptrons and generalize the classical idea of a perceptron. Or we can have convolutional quantum neural networks, or quantum neural networks that are based on the QAOA, the quantum approximated alternating operator ansatz algorithm. And all of them are different realizations of quantum neural networks. Now, of course, ever since we have quantum computers and people realize that maybe we can do something in the NISQ era with them, maybe we can just try to solve simple VQE problems and find ground state energies, or maybe we can do something more intricate, like create more general quantum neural networks, people have just created a plethora of architectures that are out there. But of course, one of the most interesting questions is, how do we know if those quantum neural networks are actually going to be useful? How do we know if this optimization loop are actually going to be able to solve this optimization? And sort of the scope that we're trying to get with our group is that these are very interesting questions that we need to solve and we need to address in order to move forward. So of course, as we know, and as I was previously saying, neural networks are very widely used today. But if we just take a step backwards and we saw their historical development, there were periods where neural networks were thought to be dead and no one was using them. And it's just because they have a bunch of difficulties that had to be overcome to get to the point where they are. Originally, for a quantum neural network, it was just created as a generalization of a neuron wherever there was just a single perception. And it was very quickly shown that this was not enough. So then people proposed multi-layered perceptions, but then it was shown that it was really hard to train them until the backpropagation method was developed. So in a sense, there were many periods where neural networks did not get all the attention they probably deserved just because there were trainability issues. So of course, the question that we have to ask is, are quantum neural networks getting to a point where we might be heading into a winter? Are there stagnation periods that we might be heading into because we don't know that there's problems that we actually need to address? So in this sense, we believe, as I previously said, that it is paramount to analyze the trainability if we want to try to avoid the winters that classical neural networks pass through, and if we're hopefully able to guarantee, at least in some regime, that quantum neural networks will be able to, in fact, outperform their classical counterparts. So now I'm speaking about trainability, and let me just get a little bit into that word. So what do I mean by trainability? How do we actually analyze this, and how to quantify the trainability of a quantum neural network? So as I previously mentioned, and let me just go back to this variational quantum algorithms and employing parametrized quantum circuit, what we have to do is train the parameters in this circuit, or more generally, in a quantum neural network. And as I said, those can be rotation angles, they can be gate positions, they can be perceptron weights. So there's many things that one need to actually train in a quantum neural network. And as previously mentioned, and I'm going to go a little bit faster here because I already went over this, we usually define what is called cost functions, or in the machine learning community, they're known as loss functions, which is a function that we're actually trying to optimize. For cost functions, we're usually trying to minimize them. For loss functions, we're trying to maximize them. So of course, whenever we have angles in a circuit, each angle will lead to a cost function value. And as we change those rotation angles or those gate placements or those perception ways, we're going to be getting different values of the cost function. And of course, that hyperparameter space of all the discrete and classical variables that we have to optimize is going to define a cost function landscape. And this is a really nice and really cool website, Loss Landscape, which actually analyzes how the landscape could look for different optimization problems. You can think about it as you have this redundantly landscape, and you're just trying to find the minimum. So for all of you that have worked in optimization, you can clearly see that in this sort of problems, and of course, if I see this, I just start cringing a little bit because there's a lot of local minima here. There's a lot of problems that could arise when actually optimizing, but the goal is to try to get to the minimum place here. And whenever I say trainability, is the ability to start from a given point around the training landscape and try to decrease the value of the cost function to reach to a minimum value. And of course, you can start to see that and just a little bit of spoilers here that if the training landscape has problems like having a lot of local minima, this could be troublesome. But also if the training landscape is just very flat, that could also be very troublesome. And let me get a little bit more into this idea of the flatness of the cost landscape.
So there is a question
Yes.
by Kunal. It's say, what is the best approach for a binary cost function?
Oh, that's a great question, because in general, yes, and this idea of this cost landscape that I have right here, you can see that this is not binary in the sense that, let's say that you have a problem of a quantum neural network that you're trying to say, is this a picture of a cat or is this a picture of a dog, right? So in this case, your output is just binary, it's just 1 or 0. So it's not going to be obvious to see how you're going to be able to define this sort of landscape. In that case, whenever you have like training data, it's usually good to look at the risk function, where you're actually going to be looking at how your neural network is going to be performing over your training set and over your general data set. And then you will have a little bit more information, and it's not going to be just binary anymore. But for the purpose of what I'm going to be talking about here, I'm going to be just referring for cost functions, which are just going to take real values. So you can see how for binary decision problems, you can map this by looking at the risk function into a cost landscape. It's going to be a little bit more complicated, but still you can do it. And this is sort of the kind of thing that we're going to be dealing whenever we talk with quantum neural networks. I'm sorry, for dissipative quantum neural networks, which is the second part of the talk. I hope this answers the question. Please let me know, Paul, if there's anything else that I haven't been saying. But in general, as I said, this cost landscape, I'm referring, for instance, to like a VQE energy, which is a continuous function, right?
Yeah, that's good. Thanks. Yeah.
Marco,
okay,
when you talk about the trainability of this landscape,
yes.
won't that depend on your optimization algorithm?
Absolutely. This is absolutely
type
true.
of the algorithm, which types of landscapes are easier or harder?
No, absolutely. So in this case, the properties that we're talking about, the trainability, about the landscape, are going to be algorithm independent. And essentially the Barren Plateau phenomena, as we're going to see in the next slide, is just a statement about your landscape being completely flat. So you're not going to be able to use any gradient-based or gradient-free optimization method that is going to be able to give you a minimizing direction. So of course, any optimization problem is going to depend on the optimization method that you employ. And actually, one of the things that our group has been working at is what are the best optimizers for variational quantum algorithms, especially whenever you take into account noise, because it has been shown that most of the classical black box optimizers that we usually employ are not optimal for quantum. Like you just take Python, your SciPy optimizer, and you use Kobila or Powell or any just black box optimizer, they will usually perform poorly under the presence of quantum noise. Even more advanced optimizers like Atom, we've managed to show that you have to take into account all the difficulties that come into quantum neural networks to optimize. But for the purpose of this talk, the statements that we're making are going to be independent on the optimization method and also in the parametrization method that you employ. Once again, I'm doing this thing of kicking all the questions to Kunal's part of the talk on dissipative quantum neural networks. But we have one result there where we actually consider 2 different optimization methods to show that the Barren Plateau result is independent of the optimization method. It doesn't matter what you're trying to do, be it gradient based or be it correlate your, try to do like line search or optimize all your angles in the circuit instead of optimizing one, you would still have a Barren Plateau. So I've been talking about Barren Plateaus, and let me just move forward. This is the work that started the whole field of what is a Barren Plateau in quantum neural networks. Of course, the trainability of classical neural networks has been greatly studied, but for quantum neural networks, it was all until this very nice work by the Google group, by Jared McLean, Sergio Boisho, and collaborators, that they were analyzing what happens whenever you have quantum neural networks. And when I speak quantum neural networks in this context, I'm talking about random parametrized quantum circuits. So once again here, you can see, and I'm sorry if I looked here, I have this monitor here. I'm talking about having some circuit with some gates that have parameters. Those are these boxes. And I have some unparametrized gates, which are going to be colored here, like this could be a CNOT. So the question is, if I take one of those gates, let's say that this is a single qubit rotation, and I want to try to see if I can manage to find a way to say, how do I have to change this rotation angle? Do I have to make it larger? Do I have to make it smaller? What is actually going to improve the value of my cost function? So for this, what we do is we just take one of the parameters, let's say this one right here, and we're going to compute the variance of the partial derivative of the cost function. So the variance is simply taking the partial derivative of the cost function, computing, squaring this up, computing the expectation value, and subtracting the square of the expectation value of the partial derivative. Now, how is this actually giving us information about trainability? Because what this is giving us whenever we have this expectation value is, in average, if I try to change this angle, how much are those values of the gradient gonna concentrate around the mean? So something that can be really easily shown is that the expectation value of the partial derivative, this term right here, is gonna be 0. And this is sort of almost intuitive because there's no preferred direction in optimization space. It would be weird if we have a circuit that is always preferable to have angles in some direction. So in general, it's almost straightforward to show that this term right here is going to be 0. And then this term right here is telling us how much in average we're concentrating around the expectation value of 0, right? So if this value is very small, if the variance of the partial derivative is extremely small, this is telling us that in average, our partial derivative is going to be 0. So that means that our landscape is going to be very flat, and hence the name Barren Plateaus. And you can see that even if you try to do gradient free or gradient based, if you just start somewhere in your training landscape and you have this flat landscape, you're essentially going to be picking random directions to optimize. So you're not going to be able to find a minimizing direction. So what the Google group managed to do is that they managed to show that whenever you have deep circuits, and I'm going to use the term deep, whenever I have a depth of the algorithm that is in poly n, the variance of the partial derivative vanishes exponentially with the number of qubits. So this is what is called the Barren Plateau phenomena. Of course, and you might be saying, okay, but I've coded variational algorithms. How come I don't see this? And it's usually because whenever we work with variational algorithms, we have a small number of qubits. But if you start to scale it up, as I will show in numerics in a bit, this is going to be really hard. And you can actually see that the variance is going to 0. So this is the plot that they did for their paper. It's a really beautiful paper. I highly recommend it. That as you increase the number of qubits, the variance of your partial derivative is just exponentially decreasing. This is a log scale in the variance, so you can see this phenomenon. Yeah.
I have a small question, like regarding this variance thing. So, I mean, yeah, recently, there came a paper where they like used the quantum natural gradient, and it's like kind of, if you use this information about the local Fisher information kind of analog, then you can sometimes do better than what you can do in, like certain landscapes and all. Like, I mean, if it's not Euclidean or something. So I'm just wondering, it might be, like naive or incorrect or something. So if like, if I put some kind of, those 1 by Fisher information thing here, like, can it help? Like, I mean, what is your intuition with respect to that?
So it's gonna greatly depend, because of course the Barren Plateau phenomenon, this is the thing about the variance, is that you're talking about in average, right? So in average means that of course you still have a global minima where your cost function has to vanish if your circuit contains the solution to the problem. So those arguments are usually using a little bit extra information. So here we're just making a statement about randomly initializing all the parameters in your ansatz. And hence, this is just an average result. Of course, if you have some extra little bits of information, these results will no longer be valid as soon as you take into account more.
I'm thinking that maybe, like, I mean, like it could be possible that if you look in the Euclidean sense, you have those Barren issues and all, but if you have the information about the geometry, I mean, the Riemannian geometry, then maybe, it can help a bit. Maybe.
Yeah. No, I absolutely agree. The problem is that still, since these are very non-convex problems, even if you compute the curvature, it's still going to be exponentially vanishing. So you do need a little bit more information about your problem that you're trying to solve in order to avoid Barren Plateaus. So this is, of course, for the brute force approach. Randomly initialize all the angles and try to find a minimizing directions, which sadly enough is what most of us are doing. And this is why we think that analyzing the trainability is very important. So I think I'm going to have to start brushing up a little bit here, but I still don't want to skip this. So I don't know if I would like to say show off of hands, but those results span from the fact that the circuit becomes a two design. So I have a slide here about T designs, but I would like to know what is the state of the art. Like, are people familiar with T designs? Is this something that I should go fast? Is this something that you want me to get into? I'd be happy to do either or.
I think it would be better if you explain T design, because not everyone is familiar with the notion.
Absolutely. Perfect. This is precisely why we created this slide. So let me just get into this intermission, because the concept of T designs is very useful. It's going to play a big role in our results. So let me explain what a T design is. And for that, let me explain what the harm measure is. So first of all, consider the unitary group, UD, of unitaries of degree D, and the harm measure is what it's known, it's the uniquely defined left and right invariant measure over the unitary group. So what does this mean? What this means is that if I have a function f of v, which is a function of my unitary v that belongs to the unitary group, and this unitary v is sampled uniformly over all the unitaries that I can have, and this is essentially what the harm measure is just you take your whole space of unitary measures and you sample uniformly. Well, it's been shown that there is just one measure that exists, or all other invariant measures are going to be related to the harm measure by at least a constant, that is left and right invariant. So that means that if I have a unitary v that is uniformly taking over the harm measure, I can multiply it by any other unitary A, and it's still gonna be uniformly taking from the group, from the unitary group. Now, the concept of T designs comes like, let's say that we have a finite set of unitaries, like so, wherever the set is going to have a certain size and it's going to be discrete. Of course, T designs can be defined for continuous variables, but for now, let me just define them for discrete variables. So what we say is that this set is going to form a T design if for any polynomial of degree T in the matrix elements of V and in degree T in the matrix elements of V dagger, we have that the expectation value over all the matrices in this set, like which we can compute like this, is going to be indistinguishable from sampling this unitary uniformly from the harm measure. And I know this might not make a lot of sense, but let me just take a step backwards to try to understand why this is important. So imagine once again that you have this parametrized quantum circuit. You have variational angles in their rotation angles. You have discrete variables that are going to be like gate placements. So what you're going to do is that you're just going to generate a set. Let me just take random angles. Let me just take different positions of all of those angles in my circuit. And let me just generate this set of unitaries. Because of course, let me just assume for now noiseless, all of this circuit right here is going to form a unitary. So for each set of angles that I have in my circuit, I'm going to be defining a different unitary V. So for different angles and gate placements, I'm going to be able to define a set of unitaries. So the concept of T design is really important in the context of quantum computing, because there's many very beautiful results like this right here that show that in many contexts, you can take, for instance, random circuits, and whenever you reach a certain depth, by just randomly placing gates between two qubits, this is going to form a two design. So this is going to say that whenever you are just randomly change the angles in my unitary and just compute in my circuit and just compute the unitary that is going to be coming out of this circuit, it's almost as if I'm sampling uniformly over all the unitaries in the unitary group. And it's also been shown for different architectures, not just random circuits. Just, for instance, we can also have results for first neighbor couplings or local couplings. So you can see that the concept of t-design is very important with random circuits. And we actually have limited, but at the same time, fairly good understanding as to when a circuit will become a t-design. And it usually involves the number of layers that you have to be polynomial in the number of qubits. So this is exactly the sort of work that the Google group was working on. Now, of course, you might be able to say, okay, this is all really cool, but if I have to have a number of layers that grows polynomially with the number of qubits, let's imagine that I have the Google's income or quantum computer that has 50 qubits. There is no way that I can do 50 layers and maintain coherence for all the circuits that I'm doing. Maybe we're getting there, but imagine that whenever we have 100 qubits, will I be able to do 100 layers? So maybe we're safe because the results from the Google group just apply for deep circuits. So finally, I'm getting into our results, which is, can we extend the Barren Plateau phenomena for shallow circuits, for the kind of circuits that we can actually implement nowadays with the quantum computers that we have? And the answer is locally, yes, we can extend this Barren Plateau. And we showed that it's actually gonna depend on how we define the cost function. And let me just go into this very simple example, almost trivial, you might say. Imagine that I have a certain number of qubits n. I just initialize all those qubits on 0, and I do on each one of those qubits a random rotation around the y-axis. And at the end, I'm just gonna get a tensor product state, but I'm gonna try to recover the old 0 state. So essentially, I'm trying to learn, if you will, an identity. I'm trying to compile and have all of these rotations around the y-axis to be identities, because then I start with the old 0 state and I recover the old 0 state. And you can think about this as some sort of log-Schmidt-Echo test where I have the old 0, I do identity, if you will, and I want to undo this identity with rotations around y. This is, of course, a toy model problem, completely trivial, but it still has some very interesting applications. For instance, if we define our cost function as just the probability of all the qubits being on 0, so I have my input state, psi naught, which is going to be old 0 state, I apply this gate sequence, and then I just measure 1 minus the probability of all qubits being on 0, you can clearly see that if this V right here is identity, then I'm going to have a cost function that is equal to 0 because I'm actually recovering all the qubits measured on 0. So this is what I call a global cost function. And which is actually what it's doing is that I'm comparing states that live in exponentially large Hilbert spaces. And whenever I do this, we can actually show that we have a Barren Plateau phenomena. This is an example of just taking a transverse cut into the hyperspace of 2 angles, and most of the landscape is going to be very flat. And we not only discovered that for even very trivial shallow quantum circuits, global cost functions lead to Barren Plateau, but they also lead to other phenomena like narrow gorges, which is that almost all the values that have cost function values smaller than 1, which is the maximum whenever this overlap is going to be extremely small, are going to be concentrated around a space that is going to vanish exponentially with the number of qubits. So this makes it even harder because this means that whenever randomly initializing, the chance of us starting somewhere in here is going to be exponentially decreasing with the number of qubits. Now, of course, locally, there's one way around this, which is let's just define local cost functions, wherever instead of comparing objects that live in exponential large Hilbert spaces, we're just going to be comparing objects locally. In this case, what we're doing is that we're taking our state that has gone through this ansatz and just measuring the probability that one of those qubits is 0. Of course, if all the qubits are in 0, this cost function is also going to be 0. So this is what we call a faithful cost function. And in this case, we see that there is no Barren Plateau and there is no narrow gorge. So we already have an intuition that the cost function is going to define how trainable our variational ansatz is going to be, even for very simple cases. And now this is very important because a lot of algorithms out there are stated in terms of global cost functions like fidelities. I have a quantum neural network. I want to prepare a state. My cost function is just fidelity between the state that I'm preparing and the state for my training set. And this could lead to problems, right? So let me just keep ahead. Once again, I think I'm on track, but it's still gonna go a little bit faster. What we do is that
Marco,
yeah.
I mean, it's fine even if, like we shoot a bit, like I think 50 minutes or something, it's fine. So it happens in most of our group meetings, and take it very casual, like it's no pressure.
No, I really appreciate it. I just have this conscience that it's 11 o'clock for some people, and if they're like me, we value our sleep. So sorry about this. I hope this is at least entertaining to the point that
I mean, we are like,
lack of sleep.
we should understand. So like, no need to rush. Like it's fine. Yeah.
Perfect. Thank you very much. So let me just get now into our main results, and I want to emphasize this, that the results that we derive in this paper are valid for what we call layered hardware efficient ansatz, which are this sort of ansatz that you have probably seen here and there, wherever we employ the architecture of the quantum circuit, where usually the entangling gates are local, whenever a qubit can be entangled to qubits that are right next to it. So in a hardware efficient ansatz, and it's called hardware efficient because we employ the set of gates that the quantum computer can naturally apply. And we don't try to apply gates which are going to have large overhead. Whenever you go to Qiskit and you use IBM's cloud quantum computer, you can write any circuit that you want. And of course, in paper, it can look very small, but whenever you take a gate that is not native to the quantum computer, it's going to have a big overhead whenever it gets converted to the native language. So in a hardware efficient ansatz, you're actually trying to minimize the depth. And it has been shown in one of the latest Google papers, which is the trying to use a quantum operator alternating ansatz. Then the QAOA ansatz is really good, but in present devices, it just doesn't work because of noise. So you actually sort of are stuck with hardware efficient ansatzes. So this is sort of what we have in the near term, this sort of layered ansatzes. And of course, we call it layers because it has the structure of applying gates to neighboring qubits in an alternating fashion, where we call this right here one layer, then we have a second layer, a third layer, and so on. So, and once again, we're going to define this cost function as just taking some input state row, completely arbitrary. You send it through your parametrized gate sequence V of theta, and you measure some expectation value at the end. And to summarize our main results, if you have a global cost function where we are measuring all the qubits in the system, this is what we schematically show here, we already know that when the number of layers is in poly n, you're going to have a Barren Plateau. And this is a result that the Google group derived. What we managed to show is that it doesn't matter how many layers you have, this is always going to have a Barren Plateau. And this is worrying because this could mean that we don't have, unless we have smart initialization strategies, our cost functions are not trainable. But luckily, we were also able to derive some positive results, which are if you take local cost functions, and in our case, local means that we're just measuring a number of qubits that is going to respect the symmetry of the problem. Let's say if those are gates acting on 1 or 2 qubits, if you're measuring 1 or 2 qubits, then we managed to derive trainability guarantees whenever your circuit depth is has a number of layers that is up to log n. Then, of course, we're going to have a transition regime when the number of layers is in poly log n. And we know that this circuit will form a 2 design whenever you have poly log n. So once again, even for local cost functions, you will always have a Barren Plateau for deep circuits. Because, of course, this is what the Google showed. It doesn't depend on the locality. Anything that you try to measure is going to have a Barren Plateau. And just a final comment, if you see this and you're a little bit worried that those results might just be valid for one-dimensional circuits, it's pretty straightforward to see that if you have two-dimensional connectivity like the one that we usually have in IBM devices, you can also apply layered ansatz. So those results are, in a sense, valid for the sort of architectures that we actually apply. Now, of course, how do we derive those results? I'm by no means going to get into all the details at this point, but we derived 2 new theorems. One of them is for completely global cost functions, where we're measuring all the qubits. And what we managed to derive is an upper bound for the variance of the cost function partial derivative. Whenever, once again, we just take an angle in these ansatz and we're trying to train. And what we find is that this upper bound, if you see this right here, is exponentially vanishing in the number of qubits. So the more qubits we have, the more this variance is going to be vanishing. And for local cost functions, which have, where as I said, we're just measuring a number of qubits that it does not increase with system size, we managed to derive a lower bound. Now, in this case, please keep in mind that having a lower bound is the key value, because if you have a lower bound, then you can have a guarantee that your variance is not going to be smaller than this quantity right here. And this lower bound is vanishing with the number of layers. Let's just forget about all the kinks and details of the proof and this term right here. Let's just look at the prefactor, because it usually contains the information that we want to look at. And you can see that now the prefactor, is exponentially vanishing in number of layers. So of course, is this big L, which is the number of layers, is in log n. Now G is in 1 over poly n, which is exactly what we're trying to get. Now, of course, those results were derived for the very special case whenever we have all the blocks in the system, all of those squares that I drew being a 2 design. But of course, we want to try to illustrate this. So for this, we implemented the quantum autoencoder. For those who might be familiar with what autoencoder does, there is a version of the classical autoencoder, which was proposed for the quantum realm by Jonathan Romero and his group in 2017. And essentially, the main idea of a quantum autoencoder is to compress an ensembles of states that are acting on a bipartite system of qubits into just one of those bipartite systems, let's just say into the A system. So essentially, I want to have all the information into this big quantum state into just this subset of qubits. Now, what we have is this ansatz right here, where you can once again see that this layer structure sort of starts to appear. Now, of course, if you just take this as one block, rotation around Y and Control Z, this is by no means a 2 design. This means that this ansatz is outside of the scope of our theorems, but still it could be interesting to see if the ansatz that we actually employ in our day-to-day still apply to the sort of theorems that we derive. And for our numerical implementations, what we have here is the cost function value versus the number of iteration in our optimization algorithm. And what you can see here is that as you start to increase the number of qubits for the global cost function, which is the reddish curve, there comes a point wherever we cannot decrease the cost function value. And this is because we're reaching a Barren Plateau where we're not able to find a minimizing direction. Whereas on the other hand, as we increase the number of qubits, we're still trainable. And you might be wondering, like, this is a little bit weird. How come you're still trainable up to 100 qubits? And this is because all of these examples were done with this ansatz right here, which just contains 4 layers, or I'm sorry, 2 layers of an alternating layer ansatz. So we can see that the results are saying this is a matter of how many layers you have. It's not a matter of how many qubits you have, because for 4 qubits, we can train up to, with 4 layers, we can train up to 100 qubits. So sort of these results, which are a little bit outside of the scope of our theorem, show what we're doing. So let me just give some brief discussions and conclusions about what I've been doing. And what I've been talking about and the work that we've been doing is that in this work, we provide results for hardware efficient ansatzes. We show that global cost functions are untrainable for all circuit depths, whereas local cost functions will have large gradients. When I say large, it means that they're vanishing polynomially with the number of qubits when the depth is up to log n. So at least we have some trainability guarantee here. And of course, here, those results, we think of them as extensions of the Google results for shallow depths. And of course, we have this idea of trying to understand how locality and trainability are connected. And of this idea of trying to compare states that live in exponentially large Hilbert states, and the probability of 2 states being very similar is exponentially vanishing. So you can sort of see why global cost functions are not so bad, are so bad. And of course, what we want to do is get trainability guarantees, and this is what we've managed to do. And of course, probably the most interesting part of that work, which was what I mostly did for 4 months, was just trying to develop this new tool set of how can we employ the wide garden calculus, which is what we use to actually integrate functions of polynomials of matrices that are 2 designs. Yeah.
There is a question from Paul Griffin. He says, did you perform your results on a quantum computer, or was it like a simulated result?
This is a simulator, and you can see this because we still don't have a 100 qubit quantum computer. And of course, once again, you might be saying, 100 qubits is a lot, it's because we had to employ, because we wanted scalability in the number of qubits, a problem which we knew that the solution had an efficient MPS decomposition. So we actually tailored a quantum autoencoder problem that we knew was scalable, that the complexity of adding qubits was just growing polynomially with how many qubits were in the system as states that have efficient MPS decompositions do. But yeah, this is not done in a quantum device.
Yeah, because one of the issues I was thinking about was just the data loading and the reading out is going to take time as well. So
absolutely.
How many goes through lots of iterations, then it's going to take a long time to do on a
yeah, absolutely. On a cloud computer, 600 iterations is going to take a while. You're going to be waiting in queue for quite a while. Absolutely. And so just as a segue to Kunal's part of the talk, those technical tools that we developed for this paper, we hope that they can be used to analyze other more general quantum neural networks. And this is where I'm going to stop sharing my screen and I'm going to leave it up to Kunal, which is going to take it from here. And thank you very much for attention, and we'll keep discussing after Kunal's part of the talk.
What are the possible future directions from here? Like, for example,
yes.
So, I mean, obviously we haven't reached at the place where we can, perfectly train, we still miss our back propagation kind of thing. So,
yes.
I mean, what do you kind of thinking, what one needs to do here to to have some practical, real thing coming out of the NISC?
So the main approach that we need to deal with, and this is one of the conclusions that Kunal is going to be dealing with, we need smart ansatz, we need smart initialization strategies, we need different tricks that will allow us to overcome the Barren Plateau phenomena. Our group recently put up a paper where they show that, for instance, correlating some of the parameters helps in order to try to avoid Barren Plateaus. You get large variances. We analyze specific cases, but still we hope that that sort of tricks will help. Also, for instance, instead of trying to train your whole neural network, you do layer by layer training. So I would say that the research is twofold. One of them, and this is what Kunal is going to be talking about, these studies about trainability are very architecture dependent. The results that you get for one architecture are not going to be applicable for another architecture. So the results for hardware efficient ansatz do not apply for QAOA. And the results that Kunal is going to be talking will not apply for other type of neural networks. So one of them is proposing a quantum neural network, I feel needs to a close analysis of trainability. Even if it's just numerics, you will be able to see if your quantum neural network is trainable. And for this, we really need to go past 5, 6, 7, 12 qubits. We need to go to the large number of qubits regime for this. And this, of course, lead us to problems of how do we do this classically. And second, we need smart initialization strategies. I think those are the two main research directions that we need to focus on. And with that, let me just stop sharing here.
Also, can one think of, okay, so some kind of robustness or something, one might, because in principle, we do not apply the actual unitary, but because of the, open quantum system nature of the actual devices, we will have to kind of look for some give robustness guarantees. So even if you don't have unitary, maybe, close to.
Absolutely. Analyze, and that's another thing, and that is current research that we're trying to do, and this is something that we've done with Kunal, is analyzing the effect of noise. Most of the algorithms that we run are noiseless, and we don't know the effect of noise. How detrimental will it be to the algorithm? Absolutely. I think that that's paramount to analyze how well will an algorithm scale up.
There is one question from V. It says, if we only measure one single qubit, do you think we have the full capability?
Well, if you're employing a hardware efficient ansatz and our results are telling you that you will be able to train up to log n depth, even whenever you have local cost functions, they will be untrainable for longer depths. So even local cost functions will not give you guarantees for longer depths. So once again, you will have to go to more smart training strategies.
Very nice. Yeah, thanks. I think probably.
All right. Can you see my screen?
Yeah, we can.
All right, should I go ahead?
Yep.
Okay, yeah, thanks for inviting us. And it's good to be in Singapore, even though it's virtually. And it's my first time in Singapore. So as Marco has already mentioned about all the basics of how you can show whether your ansatz or your training method is trainable or not, and what are the techniques, what is global cost or local cost, it makes it easier for me to go to the next part of the talk. So now, as Marco already raised this issue, whether because his results were only valid for hardware efficient ansatz, now you can ask, can we define different QNNs? Answer is yes. Now the question is, can you also study trainability for different kind of QNNs? So I'm going to discuss one of the QNNs which was defined in this paper, training deep quantum neural networks, and this is like completely like analogous to the classical neural network, which I'll explain in the next slide. And in this paper, they also argued that maybe this kind of architecture is scalable, or in other words, maybe this kind of architecture does not have Barren Plateaus. And we studied this kind of architecture in detail, and we actually show that in general, no, the statement is not correct. We find that you can have these trainability issues, which Marco mentioned. And I want to emphasize that whatever Marco discussed about Google's result initially, and then what Marco and co-authors from Los Alamos National Lab have shown for hardware efficient ansatz, those tricks directly do not apply for this kind of ansatz. So let me just go to the ansatz. So the idea is following. So we know that, can you see my cursor so that I can, all right. So in classical neural network, what do we have? We have, let's say, input layer, and then we have hidden layers, many hidden layers, and we have finally output layers. And each of the nodes in the input layer, we call them neurons. So if we want to, and also like those neurons in the input layer are connected to hidden layer through some functions, right? And then similarly, you go from one hidden layer to another, and then finally you reach to the output layer. Now, let's say if you want to generalize it to quantum case, the very basic thing or the naive thing which you can do is to start by saying that, okay, let's call these nodes as qubits. And the way you can connect qubits from one layer to another is through unity transformation, because that's the most general thing you can do in quantum mechanics. So the architecture which the authors of the previous paper I mentioned considered is as follows. So let's say in the example which we have drawn here, you have 3 qubits in the initial layer or the input layer. Now in the hidden layer, let's say you consider 4 qubits. The way you connect the input layer qubits with the next layer is as follows. You connect all 3 qubits in the first layer with the first qubit in the next layer. So you apply a 4-qubit unitary. After that, you apply another 4-qubit unitary, but now you connect first 3 from the first layer and the second qubit in the next layer. And then you just follow. So you have to apply 4 different 4-qubit unitaries. And once you have done that, then you discard the qubits from the first layer. So it is shown in this picture in the middle, which is, so let's say if you have 2 qubits as inputs and then 3 qubits as output, first you apply 3-qubit unitary connecting the first 2 qubits in input and first output qubit, and then first 2 qubit in input, second output qubit, and then so on. And then once you have made these connections, then you discard the qubit in the first input layer. And once you have gone from one input layer to the hidden layer, and you have discarded the input layer, then you try to connect the hidden layer, first hidden layer with the second hidden layer, and then discard the first hidden layer. So that's the reason why we call it dissipative, because you are discarding qubits in this kind of architecture. And this is also the reason why it's different from the hardware efficient ansatz, because as Marco discussed, that let's say if you start with n qubits in hardware efficient ansatz, then you apply these parametrized unitaries, that is single qubit gates and C-naughts, but then you never discard any qubits. You just apply layers of these parametrized gates. And at the end, you get an output. And I think this was some sort of a hope that maybe if you add this kind of dissipative nature in your architecture, then maybe it can avoid Barren Plateaus, because essentially you are dealing with n qubits, and let's say in the next layer also you have n qubits. You apply these transformations, got rid of these n qubits, and you are again left with n qubits. So you're not like, in each layer, you're just dealing with 2 layers at a time. So this was the hope that maybe this can avoid Barren Plateaus. But now, even though we have defined this architecture, or let me just briefly mention how we can define it mathematically. So as I said that you start with some input qubits, so let's just call it rho input. And when I say that you have to connect it with the first hidden layer, so you have to assume that all the qubits in the hidden layer are initialized in the 0 state. And then you apply these unitaries. And you can imagine that you can, as I was saying, that you could discard the qubits from the input layer and then first hidden layer and then second hidden layer. You can do this tracing at the end. So you can mathematically define it as if you started with rho n and applied and started all the hidden and output qubits in 0 state, and then applied this B. And then you traced out all the input qubit and hidden layer qubits. All right, so we have the architecture now, and now we can ask about what are our goals. From this kind of architecture, what do we want to learn? We can try to mimic what we do in classical machine learning or in the classical neural network, where someone gives us training pairs. So what do we mean by training pairs in the quantum context? What we mean is, let's say you have some input states, which is denoted by phi x in, and x is like your different input states. And now you can ask, do you want to find out a transformation which takes you from phi x in to phi x out? So let's just assume that that transformation is a unitary. So our goal, so the training pairs are defined as phi x in and you acts on it, and you get a phi x out. And the whole goal of this kind of architecture, at least for the context we are going to study, or we studied and I'm going to present, is to learn U from these training sets. So now once you have set the goal, you have to define a cost function. So one of the ways to define a cost function is to define in terms of fidelity. So suppose if I start with phi x in and I apply this parametrized circuit, this DQNN, and finally I'll get some state which is rho out. I can ask this question, what is the fidelity of this rho out with the phi x out, the ideal state I should have prepared instead? And obviously, I mean, to have the cost function go to 0, we define it as 1 minus fidelity. So this was defined just for one state, right? So if we have, let's say, n pairs in my training set, so I can take the average over all these n state. So this is how we define the cost function. And you can see that if I'm defining, yeah, do you have a question?
Yeah, would it be that this cost function would be a global cost function now?
Yes, yeah, that was my statement actually next.
Over all of them, okay.
Yeah, so you can see here that this is a global cost function, and it's a very nice question that how do we define a local cost function when the task is to prepare some fixed state? So for example, you start with phi x in and you want to go to phi x out. How do you define a local cost function? So the answer is that in general, it's not trivial how to define a local cost function. But suppose if you put this constraint that the output states has to be, let's say, product state or tensor product state over all n qubits. So if you put this constraint, then it's easy to define a local cost function. Why? Because you can ask that, okay, if it is a tensor product state, then I can look for preparing the state on this first qubit, the state on this second qubit, because it was a tensor product state. There was no correlation. So in that situation, you can define a local cost. And actually, we studied that part as well, which will come in the next slide. So I think the main message from this slide, which you should take, is that DQNN is very different from hardware efficient ansatz. And this is like the first time when a circuit where you discard qubits has been studied in the context of trainability. So in this picture, I was saying that you connect all qubits from one layer to one qubit in the next layer, and you just do it sequentially. And I should also emphasize that since unitary operators or matrices are not usually commuting, so you have to set an ordering, like which unity do you apply first. So in this picture, I'm saying that I connect 3 qubits with the first qubit, and then I connect 3 qubits with the second qubit. So you have to fix an ordering. So in our work, our analysis, we fix this ordering that you do it in this order, like from top to bottom. Now you can also define different kind of perceptrons, right? Because as I said that I was saying, connect all qubits from the first layer, one qubit in the next layer. but that's like global perceptron because you're connecting n qubits. Let's say there were n qubits in the first layer. You're connecting n qubits from the first layer, 1 qubit in the next layer. That is like n plus 1 qubit unitary. So you can also define local perceptron where you just connect some of the qubits from the first layer and 1 qubit in the next layer. And maybe this local perceptron, as I'll mention later on, that it can lead to trainability regime. And this kind of local perceptron can also be useful. Let's say if your system has some sort of locality in your states, and there is not like global entanglement present in your states. So let's look at our results. So as I was saying that you have to connect the qubits from one layer to another using unitary transformations. But now you can ask one more question. How do I apply those unitary transformation? Well, one way to apply is what Marco mentioned earlier, that you can parametrize those unitaries in terms of these single qubit and 2 qubit gates, or the hardware layered ansatz. And as the question was asked, if you look at the equations, I mean, this is taken from our paper, so forget about the numbers, but just look at this OXG, which you can see that it's a global cost function because we're talking about a state on all qubits in the output layer. But you can also define a local cost function if you assume that your output state has to be a tensor product state. And this is what I was mentioning earlier, where you just do the averaging over the states on each qubit individually and try to find fidelity for those states. So now let's say once you have defined these cost functions, global and local both, now you can ask this question, is this kind of architecture trainable given that your training method is based on this parametrized quantum circuit through the hardware efficient ansatz? What I mean is that, as I was saying that you have to connect qubits from one layer to another using unitary transformation, you can ask this question, how do I apply these unitaries? And we are saying that, okay, you apply these unitaries by breaking them in terms of layered hardware efficient ansatz. And you can show that it does not matter what cost function you start with, whether it's global or local. For both cases, you get scaling, which is exponentially vanishing in number of qubits. Here, n is number of qubits, which implies that your architecture is untrainable. And here we are assuming the same, I mean, we are making the same assumptions which Marco mentioned, that these unitaries have to be 2 design, because I mean, so far, whatever analytical results, except I'll talk about later on, the way to avoid Barren Plateaus, they all had this assumption where your unitaries have to be sufficiently random to get any analytical solution. In other words, they have to be 2 design, which Marco talked about. So yeah, this is the result for this kind of ansatz. Now you can also define local perceptrons. So, and this leads to trainability answers. Sorry, do you have a question?
Yes, Kunal, we have a question here in the chat from Paul Griffin again. Does discarding mean reusing the bits?
Yeah, okay. So theoretically, you can just assume that you just discard them and you just bring fresh 0 states. But yeah, practically, you can imagine that after discarding, maybe you just again start them in 0 state. You use the same qubits. But I mean, I would not comment on how to do that experimentally, but yeah, theoretically, you can assume that you can do it.
Yeah, if I might just say something, the problem about reusing the qubits is that you will have to repeat your experiment an exponential many number of times because you need to average over all the results of the qubit measurements.
Yeah, so you can just reset the qubit and then carry on. I was thinking maybe you could use a swap gate if you had the data on a different layer.
Yeah, so this is what I'm going to mention in the next slide. So let me just go here. So yeah, I mean, as I was saying that you can also define the notion of local perceptron where you're not connecting all qubits from one layer to the next, but rather you're connecting some qubits from the first layer to the next. So one naive way is to, let's say, if I had, let's say, n qubits in the first layer or input layer and n qubits in my output layer. And I can say that I'm just connecting 1 to 1, like the first qubit in the first layer and the first qubit in the next layer. And suppose if I connect them in a following way, as it was just raised, that you can just swap them and then apply and Y rotation. And this is like a very simple case where what you did, you just swap these qubits and then apply a Y rotation. and you can try to study what is the scalability for this kind of architecture. And this is a very simple example. I mean, you can just do it using pen and paper. And this is a shallow circuit because we are not assuming that it's a deep circuit or it's a two design. And for this shallow circuit, you can show that even for a, such kind of shallow circuit, you will have Barren Plateau for global cost if you define a global cost for such a simple architecture. Now, another question is, can you say more than just this simple example? The answer is yes. If somehow you can transfer the problem of DQNN to hardware efficient ansatz, then you can use the results which Marco already has explained. So the idea is that using these different layers in the DQNN, you try to connect them in such a way that effectively they are representing hardware efficient ansatz. So, I mean, I can go through this in detail if we have time, but the idea is that you try to apply unit trees between one layer to another in such a way that when you have gone through this whole DQNN, you effectively have applied a hardware efficient ansatz. And for hardware efficient ansatz, Marco has already mentioned that they are trainable when you have local cost function and up to log n depth. So in other words, DQNN are, I mean, they are at least as expressible as hardware efficient ansatz. And that's why we can use the results directly for, I mean, whatever Marco has already explained. As Marco was already discussing this, I mean, someone asked this question that whether the different training methods can help you. So this is one of the methods to update your, hi, yeah.
I have one question. So like, so you said that, so like, we have these issues of, you know, like trainability. I mean, as you mentioned, like in different cases and all. And and you are saying that one of the hope you are saying that map it to the hardware efficient ansatz, and there, you know, like when you have the local cost function, then maybe you can get some trainability. So like, are there other you know, like non-trivial possibilities that one can look, you know, like apart from like, yeah, like I mean, any comment with respect to that?
Yeah, so that's a great question, and that you can think of as an open question, whether using this kind of architecture, can you come up with something which is different from the hardware efficient ansatz and show explicitly analytically that it will be trainable? Yeah, so that's a very good question. Is there any other question?
No, I think we can continue.
All right, so as a Marco already raised this thing that even though if you consider a different way of updating your parameters, remember that when I was talking about the previous theorem for this DQNN architecture, there we were assuming that you will break down each unitary in terms of these layered ansatz, and then you will update through this gradient descent method. But now let's assume that instead of updating parameters, we actually concatenate the unitary with another unitary. So let's say at time t equals to s, you start randomly with this unitary v, and when you go to time s plus epsilon, you concatenate it with this unitary where h is some Hamiltonian. Now for this kind of ansatz, also what we could show is that no matter whether you define a global cost or local cost, you will still have this exponentially vanishing scaling of the variance of the gradient.
Like, do you have any what kind of h you can have here?
Sorry, what?
Do you have any constraint on what kind of Hamiltonian you have here, like local Hamiltonian?
Yeah, I mean, in this case, we just have the constraint on the Hilbert-Schmidt norm of this Hamiltonian, which is that it should be less than or equals to 2 to the n. If it is followed, then if it is followed, then we have this exponentially decreasing variance or vanishing gradient. So just to emphasize that even though you started with different way of updating your parameters, you still get the Barren Plateau issues. So I think with that, I can conclude my part. So what we have shown that, okay, we define, Tobias and his co-authors, they defined this dissipative perceptron-based QNNs, which was like direct, which were very analogous to classical neural network, where you have input layers, hidden layers, and output layer, and you connect them through functions. In quantum case, functions are unity transformations. And now if you consider perceptrons, which are global, which means connect all qubits in one layer to one qubit in the next layer, you might imagine that it's important to do that in most of the cases, because in some sense, you want to carry forward the information from one layer to another. And if you make your perceptron very local, then you might just lose a lot of information, at least in the quantum context, because they could be, that your input states could be very correlated. In classical context, it might make sense because it might happen that, let's say if it's a cat picture or dog picture, maybe there are correlation at a local level. However, let's say if you have quantum states where you already know that there are local correlations, not like very global correlation, then you can define local perceptrons. And as we have shown that you can show the trainability of those architectures. As I already mentioned, that neither of Google's and neither of Marco's previous paper results directly apply here, because you discard qubits, so you have to come up with new tricks. Essentially, we derive some kind of recursive process where you apply one technique and then you just use it again and again up to your final layer in your DQNN to get the final result. And as Marco already raised this point, that to get the trainability, you have to argue in some sense through locality. So the local cost function and then locality of your ansatz. So that also holds in this kind of DQNN. At least for the results we have proven. And as I've already mentioned, that DQNNs are at least as expressible. And our hope is that they are more expressible, because we could translate them in terms of hardware efficient ansatz, but I think they are more expressible, and then more study is required to find ways to avoid Barren Plateaus. And I think the last point is, what are the ways, as Kishore was already asking, that what are the ways to avoid Barren Plateaus? One thing is, let's say, as Marco was explaining, that these results hold only when you have deep circuit, or for example, for hardware efficient ansatz. If it is deep circuit, when does it become deep, or when does it become too design? Is it when it's like the poly n depth? And maybe instead of updating your parameters for the whole circuit in just one go, maybe you just do it slowly. Like maybe you just do it for a small section, and then you add another more layers. Smart initialization, because maybe if you have, let's say what Kishore was raising earlier, that if you have some more information about your system, maybe you can start close to the global solution, global optimal solution. And recently, Tyler, who is a postdoc here, and Patrick, they uploaded a paper where what they were considering was, they considered parameterized circuits, but some of the parameters in that parameterized circuits were correlated. In other words, they were initialized at the same value, and they were also updated with the same value. And it turned out that if you do such kind of tricks, then you can avoid Barren Plateaus. And I think we have to come up with more smart techniques to avoid Barren Plateaus if we really want the variational algorithms to be successful in the NISQ era. And with that, I think both Marco and I thank you for your attention, and stay safe from coronavirus.
Yeah.
Thank you.
So Kunal, it seems like, again, looking back at the history, we don't want the winter, right? So we had this feed forward networks, the regular ones, and then came the CNNs. And when the CNNs came, they basically, this cat dog recognition thing, it went to another height. And obviously, and people are trying to get better and better optimization techniques, don't use SGD, try Adam, try momentum, try this, that, and all. So, we are kind of, I gather from here that, there are a few frontiers that we have to, work at the moment, is that the optimization function, the optimization, how do you put your objective function, the first thing. The second thing, obviously, how do you initialize your parameters? And then what kind of architecture you can have, and whether, this kind of things correlating parameters, or
I think, it is open on all fronts, whether defining your architecture, whether just defining in terms of hardware efficient ansatz or defining in terms of this dissipative, and then defining the cost functions. So, I mean, from both talks, I mean, Marco's and mine, you can see that local cost functions help. And then the final thing is that how do you, like, I think going completely random is not useful. That's the main message. So, and that's but then the issue is that, let's say, if I don't have any information about my system, then there is also no way to start smartly. So I have to start with like random initialization. So it's like, maybe if I know about the system, I can come up with ways to avoid Barren Plateaus. But if not, then we have to come up with other ways. Yeah, if I cannot use the system information.
You can think of this thing as physically, like, I mean, so like can you think of this local like cost function as something that you are kind of moving very carefully, you know, like by tuning things, like, I mean, I don't know, I mean, like, maybe you guys could.
I think for that, I think the picture which Marco showed was very helpful, because it has to do with the landscape. So I think Marco had a picture, right?
It not only has to do with the landscape, it has to do with the fact that, and let me just quote this, Hilbert space is a very large space. So whenever you're trying to converge things that live in exponentially large Hilbert space, and you just take the zero state, randomly initialize a circuit and create a random state, the overlap that you're going to have is going to be exponentially small. So it's always going to be hard to compare things that live in exponentially large Hilbert spaces. So the idea of local is that you're comparing them locally. Now, of course, as you guys were talking before, it becomes a problem of, can we actually define a local cost function? And there might be tasks for which this is straightforward and tasks for which not. So once again, these results are valid for those architectures. For instance, if you think about QAOA, there's numerical works that show that the variance of your circuit, as your QAOA number of layers increases and you cover larger sections of your graph, the variance goes up. But of course, we cannot implement QAOA nowadays. So there's always a trade-off. I mean, there's no free lunch, right? And if I may just look at some of the questions, I see one question that is saying, are there any alternative approaches for finding minimum values without calculating derivatives of cost functions? Yeah, any gradient-free optimization method will usually work, because in a nutshell, when you're using hybrid quantum computation, your optimizer is completely agnostic from the fact that this is quantum, right? It's just a function that is trying to optimize. So any optimization method works. It just happens to be that for quantum, it is, one, easy to find partial derivatives, which is usually not the case. Of course, at least for parametrized quantum circuits, you just do parameter shift rule and you can exactly compute partial derivatives. And second is that, at least from numerical evidence that we have gathered in the ICANS paper, where it's the Schotz frugal optimizer, in the presence of noise, it does seem like employing information about the partial derivative, it is useful. And Kunal, do you want to say something about the second question? Is any thoughts about how this method is to noise?
Yeah, I mean, so far, whatever we have studied, they were studied for the noiseless quantum circuits. But you can imagine that with noise, it might even become worse in some sense. Because, so for example, let's say if you consider the scaling, let's say if you consider local depolarizing noise, you know that if you apply depolarizing noise, you get this factor P on your state, and also this 1 minus P times identity. And you can imagine that you get this factor of the noise if you apply, if you consider this noise after every gate. So along with your scaling analysis, whatever we have done, you also get this factor in front of your analysis or your final term. So in other words, I mean, our intuition is that if in presence of noise, the scaling should become worse. But then I think in the noisy case, it has not been analyzed very carefully. And in our results were for the noiseless case. Maybe Marco, you want to add something?
No, absolutely. It is still an open question, like what happens in the presence of noise. And this is, again, coming back to the comment that you made, which is analyzing trainability in the presence of noise. It's going to be harder, but once again, it's going to be necessary. And maybe the main takeaway that we want to leave you all with is that don't take for granted trainability. The 6-qubit implementations that you have done might work, but it's not obvious that it's going to scale up. And I remember this from from a couple of people that I have talked with, that, and me myself, I think that we usually do what we can do in our simulations, which is small number of qubits, but just be wary that the results that you get there might not be representative of the hard cases whenever you scale your system up. So analyzing scalability and trainability is going to be necessary in order to guarantee that we do have an advantage. And of course, this can put bounds on, okay, we need to get noise level up to this point for us to get a trainability guarantee, or we need to be able to use this and this. So I think, and this is a cool thing, is that the field is very young, and there's still like many results to be found. I don't think there's too many, at least analytical or even numerical results analyzing this. So I do think that we have a lot to say about trainability of quantum neural networks.
Yeah, and just to add that if you come up with any algorithm, let's say near-term variation algorithms, and if you're going to use hardware efficient ansatz, then make sure that you also design, if it's possible, also design a local cost function. Yeah, because because the results, like whatever Marco was discussing, the results are valid for local cost function. I mean, it is quite general, but it might happen that for your specific algorithm, you cannot define a local cost function. But if you can, then you should definitely define it, because that can lead to trainability for at least log and depth.
Right, thanks for that. And yeah, actually, I was also thinking about noise in the data, whether you've got a noisy data source or whether you've got quite a clean data source. You know, some neural network designs are better for noisy data, some are for clean. Is there any thoughts around that at all?
So there has been some work done regarding this, and specifically for the dissipative quantum neural network, Tobias's group, they actually very recently put up a paper that is called the quantum no free lunch theorem, I believe, in which they use this dissipative quantum neural network architecture to look at what is the scaling of how many points in your training set you need to actually learn a unitary. And of course, the result is what we expect. You need an exponentially large number of training points to learn an exponentially large unitary. But at the same point, they analyze what happens if some of that data is corrupt and has noise in it. And they see that there are thresholds in which if your training set does not contain up to a certain point of noise, you can still train your unitary. After a certain point, it becomes untrainable. Of course, the result is just binary, right? Either your training set is perfect or either it's binary. They don't consider like intermediate, like a little bit noisy state, because it becomes harder. But yeah, I think that's the only result that I've seen about that. And I don't think there's a lot of study regarding how noise affects trainability.
Okay, thanks. Yeah.
Are there more questions?
Yeah, I was thinking, in your protocol, you always have hidden states that are really separable states, 0, 0. Have you ever have you ever thought about using entangled states for those hidden layers?
In our analysis, no, we did not consider them. But you can also, yeah, I mean, I think generalization for that case, it doesn't seem to be trivial, but yeah, we did not consider any entangled state in the hidden layers.
Yeah. So I said that because, yeah, sorry, Marco.
No, please go ahead. Please go ahead.
No, I said that because typically you can, just for unitary evolution of circuits, where you look at the depth of a circuit, typically if you can attach ancillary states that are entangled, then it can be shown that you can actually reduce the depth of the circuits. So the sort of states that you usually attach as resource.
So I just want to emphasize on one thing, that in the usual quantum computing protocols where we include ancillars to help, let's say, in the quantum computation. In this case, what is really happening is your ancilla qubits actually become system qubits. So you connect your, let's say, initial system qubits with ancillars, but then after that you discard system qubits. So it's a little bit different from the usual consideration of ancilla qubits. Yeah.
But in those cases also you discard qubits.
Yeah, no, I would
Yeah,
say
but
I would say this is very interesting, and it's one of those smart ideas that could help change the trainability of the quantum neural network. What we did was take the way that it was originally proposed, and specifically it was because they had this claim that maybe this architecture would help to avoid Barren Plateaus. So we just took the recipe that they proposed and try to go forward from them. But I think that's a really smart idea. It could be that this is one of the things that could avoid trainability issues. It's, once again, I think it's about running numerics and getting a little bit more insight. But yeah, thanks. That's a really good idea.
Yeah, and I think from our proof techniques, I do not see an easy way to just generalize it. So it should be quite novel to try that question.
Mm-hmm.
So let me know if you have results.
Totally will. Thank you very much.
Yeah. Any more question?
Well, I would have a couple of questions.
Mm-hmm.
One was actually about this discussion about noise, and you were saying that if you add a little bit of noise to the as in you have a noisy NISQ device, then it's not clear how these results generalize. But you also talked about this dissipative neural network, and that is a noisy operation there. So you have clearly you do have some results there. So what makes that so different from uncontrolled noise, if you will?
So here in the dissipative, you can see that even if there is noise, there is specific structure to it, right? We are assuming that the noise is coming by just discarding qubits.
Yeah.
So specifically, the results hold for only this kind of architecture. We cannot say that if you add in between depolarizing noise or additive, amplitude damping noise. So yeah, it's still open. I'm not sure how it changes for those noise models.
But so
Completely agree.
I would think that then it's not really necessarily a fundamental problem, because
yeah, in principle you can analyze it, but let's say it has to do that you have to define the noise model and then just go on with your analytics. But then the issue is that maybe we have to come with new tricks, I think, for that analysis.
Yeah, once again, I think that, as Kunal said, noise will just make trainability and trainability scaling worse. So in the noiseless case, we can show that even without noise, it's still hard to train. Noise will just make it a little bit harder. But yeah, I agree that this is one of the things that we haven't thought about. And if you have any good ideas to how to implement our noise and try to go about it, would be super happy to discuss.
And it could happen that maybe like if noise is changing the cost landscape in such a way that it might make it trainable. Like it could happen. We don't know.
There's actually one paper there's one paper by John Knapp that actually studies how a little bit of noise can help you get out of local minima. And it's just this idea that you can think about noise as fluctuations. So if you're trapping a very small local minima, it can just take you out. So yeah, there is some evidence that noise could help in small doses.
But yeah, again, it's difficult to put them in the analytical framework in the sense of this, deep circuits.
Yeah, no, that's right. The other question I had was, I really like this idea of the local cost functions, and seeing your figures, it makes it very intuitive why they're beneficial. But I was just thinking, this is not a proper question per se, but I was just thinking around this, that you were saying that you can define a local cost function when the output states are separable, right? Because then you look at piece by piece. But and I suppose if you can have blocks which are entangled, and then you look at sort of intermediate cases. But in these kind of quantum supremacy experiments, like boson sampling and random circuit experiments, you are looking at very entangled states, and you're interested in statistics coming from these very entangled states. So there, in that kind of scenario, you wouldn't be able to do this. And that's the kind of scenarios where we know that we get a quantum advantage. We get an advantage from using the quantum circuit. So is there anything you can comment on this? Or do you think there are some useful things that you could do with this kind of separable states?
If I might say, for instance, having an entangled state is generally not a problem, because the thing about variational algorithms is that they're task-oriented programming, right? So if you think about VQE, you can have a very entangled state. It's just about the locality of your Hamiltonian. So I would say it really depends on the problem that you're trying to solve, if you can define something local or not. So for VQE, if you have this very complicated Hamiltonian and you just expand it into poly bases, it might, I don't know, like hydrogen, lithium have like 100 and something terms. All the local terms will be trainable. So in this case, you might have like a highly entangled state, but the expectation value that you're computing in those cost functions always going to be a Hamiltonian, right? So I agree that there will be some problems whenever you have a fidelity with an output entangled state, which you might not be able to define on local cost. But for other applications, you might, I think it's going to depend on the task that you're trying to solve.
Yeah,
Right,
I
yeah.
agree. So when I was saying that you cannot define for arbitrary state, it was only for the task of learning the unitary and getting some fixed output state. And as Marco mentioned, that if your task is to find energy, let's say for any chemistry problem, then you can define the local cost.
Actually, I have a comment on that. In the earlier days, when people were looking at cluster states, people define what's called localizable entanglement. So in localizable entanglement, essentially you trace out just about all the qubits, and then you look at the entanglement of any leftovers. So I think that ideas of that a highly entangled state you can't do localized measurement might not. Well, I mean, this sort of localized cost somewhat mimics those.
Yeah. So, I mean, my answer to that is, in our analysis, our goal is to define faithful cost functions. So what we really mean is that our goal was to, let's say, prepare phi x out, right? By starting with phi x in. And let's say phi x out was an entangled state. And if you try to train it only locally on this entangled state, you might not reach to the global optima point by just taking the information locally in this entangled state. So on the other hand, if it was a tensor product state, the optimal point for the both cost function is the same. And that's why like both cost functions are faithful, or the local cost function is faithful, which means that the optimal point of the local cost function is same as the optimal point of global cost function.
But also
so that was the only reason, yeah.
But also relating to whenever you have states, you can always take a state, trace out some of the qubits, and the higher you have local entanglement, the better this is going to be an approximation of your full state. So that's true. You will have some states in which you will be able to define cost functions, which are not going to be faithful in the sense that you're just going to be looking at a substate and you're going to be losing information. But yes, this might be another smart training strategy where you have approximately faithful cost functions that you're going to be using to train until you're close enough that you can transition to a global cost function. And this is sort of one of the approaches that we have for one of the other manuscripts that we're working with for diagonalizing states, which we call variational quantum state eigensolver, where we start with some local cost function, and as the optimization goes, we transition into a global cost function. But yeah, there might be some states where entanglement is localized, where you will be able to approximate local states.
Yeah.
Any more questions?
Yeah, I think, I mean, thanks for the nice questions. There were many nice questions.
Yeah, discussions were really nice. Thank you all once again. Thanks Kishore and thanks Hermione for inviting us, and everyone for your attention. You've been a really lovely cloud, and please stay safe during these troubled times.
Thank you.
Thanks a lot.
Thanks. It was an amazing talk. We learned a lot, and thanks for taking us through these two papers.
Yeah, I mean, thanks for listening patiently and asking nice questions.
Right.
Yeah, this has been very, very educational. Thank you.
Thank you very much. Well, have a great night/day for wherever you're on the world.
All right, see you again.